Hi all, it's Mr. Yeager for chemistry. We're looking at states of matter now, which I know might be silly. It's kind of weird doing this so late in the chemistry year, but we are, again, looking at this from an energy perspective of why the states of matter are the way they are, how the particles move, how they, what are the different state changes, and are they endo or exothermic reactions, or, we'll say reactions, physical reactions. As they're going through it. So here we go. So the first thing we have to bring up is this thing called the kinetic molecular theory. So this is the basis of why the particles are doing what they do, how they act as the way they do, et cetera, et cetera. Okay? So there's three parts. So kinetic molecular theory is that matter is composed of tiny particles. That's atoms. I mean, that's compounds and stuff like that. So we've been through that part quite a bit all year. The two parts that we're getting a little bit more interested in is that particles are in constant random motion, okay? That is the kinetic part of this theory, okay? That the particles are in motion all the time. There's not a single particle in the world that is completely at rest. We might perceive the object at rest, but the particles themselves are still at least vibrating in some form. And then we have particles will interact with each other through attractions and repulsions. We've obviously been doing that. That's the intermolecular forces obviously getting involved, all right, that they do bounce off of each other, that they get attracted, they do hold together some, and that helps them form different states of matter, okay? If they start getting too fast, though, they're going to repel, and they're going to form other states of matter. All right, so part of this goes with the idea that, therefore, particles move faster as the temperature increases. We talked about it in the prior video. Temperature is the average kinetic energy of the particles. So if it goes up, obviously the particles move faster. All right? But the other part is, when the particles collide, they're going to transfer this energy between each other. So that's what we also talked about too, where I said a person standing outside on a hot day starts feeling warm because they're being bombarded by the particles, the air particles, which are heating them up. Vice versa, when it's cold, their body is vibrating faster than maybe the particles in the air have, and therefore they transfer that energy to those particles and you feel cold. So, going through these different states of matter, which you should know, but these are kind of the general properties we like to give to each state of matter. All right, solids have a definite volume, they have a definite shape, they have high density, and you cannot compress them. Okay, in other words, you can't make them any small. I mean, if you do, you're breaking them. Okay, so they will maintain their shape until you break it. Okay, essentially. Liquids, they still have a definite volume. I mean, you can look at water bottles and go, this much volume of water is in it. We can measure that volume very clearly. They take up a certain amount of space. But they change because they do not have a specific shape. They will take the shape of whatever they're in. Okay? They will take the shape of all the different water bottles we have. We generally say that they have medium density. That's a generalization, but we're going to say that they have medium density. They're not as dense usually as solids. There are exceptions. And then we can slightly compress liquids. All right? The big idea there is when you're looking at solids, or wait, I'll use the liquids. Liquids is easier to see. Liquids, there's maybe a little bit of space in between the particles. Just a little, not a lot. Like there's sometimes maybe a little bit more. And again, this is super, super minute scale, subatomic scale. All right? But you are able to possibly push those particles ever so slightly together to try to decrease that space between them. That's the idea of slightly compressible. All right? Solids do not have any space. They are in a rigid particular spot. You can't push them away from that. Gases, we basically say they do not have a specific volume. They can if you have it contained in a specific container, but we basically say that they have no it's not a clear volume. They clearly do not have a clear shape. They take the shape of the container they're in as well. They spread out everywhere, so they're like liquids in that way. They have low density because there is a lot of space, and they're very compressible. The big thing about a gas is one of the things as chemists we usually do when we're trying to identify a substance is we almost always try to vaporize the chemicals because that will separate out every possible chemical in that solution, in that mixture, into its own gaseous form, and then we can separate those gas particles based on how fast they move, because obviously smaller particles will move faster, slower will move slower, or sorry, larger will move slower, obviously slower will move slower. All right, but they are completely separate and individual from each other. So gases are always the most purest form of any substance, okay? Clearly they have a lot of space, which is why if I want to shove this down and push down on this, okay, I can shove all those gases closer and closer together, okay, and obviously pressurize the container. All right, so here's just another picture kind of showing you the different shapes of it. Obviously the solid would have its distinct shape in that container. It's not going to go ahead and change in any way. The liquid will spread out along the bottom of the container. Obviously it'll still stay together, and then gases completely separate from each other. All right, so state changes. Let's go through all the different state changes. Hopefully you know melting. Solid to liquid is melting, okay? The energy required to change a solid into a liquid we call the heat of fusion. Whoops. The heat of fusion. All right, which we're going to look at in another video in a moment. Okay, the heat of fusion. Melting because you are adding energy. Solids have less energy than liquids. All right, so that means you must be adding energy to melt it. This is kind of odd. Melting is an endothermic process. That's something people get confused by because they're like, no, I'm heating it. I feel the heat, okay? But the solid is having to pull that energy in to loosen up the intermolecular forces, okay? I'm going to actually include that. What happens during this is you are loosening the IMF, okay? The forces that are really holding that solid completely together, you are loosening them. You don't completely break them because the liquid want to stay together still, but you loosen them, and that's the energy needed to do that, is the heat of fusion. We have vaporization. That's going liquid to gas. That's called the heat of vaporization. It is also endothermic, and that's because now you are completely breaking the intermolecular forces. So we'll see this in a little bit. The heat of vaporization is going to be much larger than the heat of fusion, because the heat of fusion, you're only loosening the particles. In the heat of vaporization, you're completely breaking the intermolecular forces between the particles. All right. Other state changes, you have sublimation. That would be solid all the way to gas immediately. That's for some chemicals that have a very small window of being liquids. They don't have a lot of intermolecular force as a liquid, and so it's pretty much going straight from not just loosening, but breaking the solid into gas. And then we start going backwards. Freezing is when you're going liquid to solid, and therefore that's an exothermic process. So it's kind of reverse thinking to people. But it's the idea if you're absorbing energy, that's endothermic. Melting, boiling, or vaporization and sublimation require energy. Freezing, you're trying to release that energy. Condensing and deep deposition, those are your other two. Gas to liquid, deposition, gas to solid. All right? So, this is what you got with it, going through all of them. All right? You have freezing to melting. Again, this is endothermic. This is endothermic. I know it has evaporation. Evaporation, vaporization, and boiling are all, I don't want to say it. Vaporization and boiling are the same thing. Evaporation is not, so I'm not going to say that. I don't like when they says evaporation, but we're going to include that when you do the problems. But those are all endothermic. Sublimation would be endothermic. Going back to solid would be exo. So as you get closer to solid, that is an exothermic reaction. Okay? And that's it. Short video. Woo!